is lesson 5, Saduma here. This is going to be the last bit of what I would call the introductory part for functions and relations of Unit 2 of the diploma program. We have introduced the basic parts of this unit, except that normally the basic part that we've talked about so far is usually not discussed in the diploma program, and most teachers in the diploma program will assume that all students have discussed relations and functions and those basic ideas, including notations and equations and so on. So now that that is done, today we are going to concentrate on the definition of functions and a few other things, look at some examples before we move forward. Today's lesson is really where we begin this unit in the diploma program. And even then, in the diploma program, we move a bit faster on the assumption that most students already have a general idea of what we are discussing. So you want to take this seriously. The other thing I want to say is that in the diploma program, for those students who are studying mathematics, analysis, and approaches, the calculus program takes up about 55 to 56 hours of the 240 hours, which means that it takes the bulk of the course. So calculus together with functions and a bit of algebra takes the bulk of the course. And so this is an important area for any student wishing to study mathematics at AA. You want to take this extremely seriously, as everything is going to have a basis on this. All right, so what are we going to learn today? Some of the inquiry questions we're going to treat are just 3. Very briefly, what is a function? We want to know what a function is. Okay. Is a function the same thing as a relation? We want to be able today to split this up and discuss what functions are and what relations are and how they are related or how they bear upon one another, and if relations affect functions and vice versa. All right. The third question that we want to be able to answer is, how do we identify functions? In fact, the bulk of the task is going to be identifying function and manipulating some of the function, what we refer to as evaluating functions. Okay, so let's see. So those 3 are going to be our inquiry questions, the areas we are interested, the questions we are interested in answering. From number 4, these are now the content, the things we need to understand, right? So we will define functions. Okay, number 5, we will identify function and use the so-called vertical line test, or also sometimes called the pencil test, because for a student in an exam room, you're likely to check whether a function is, whether a relation is function or not with your pencil inside your, in the exam room on your desk, right? So you're likely to use a pencil to test. So sometimes we refer to this as the pencil test, okay? Point number 6 there. We will reintroduce the function notation. We've talked about the relation notation. Turns out this is really the function notation. You have met the function notation in one of its various forms. You've already met this before. You probably just didn't know it's called the function notation. We will get into this proper. And then we will tackle some questions, some of which I will solve myself as examples, but I will also leave some of them for you to take care of, all right? After lesson 5, if time permits, we can have one lesson where we solve those questions that I left out there for you to solve before we move on to lesson 6, okay? So let's get started, and the first thing we do is to give an overview, just review what we have looked at before, and what we've done in lesson 4. Generally, in fact, the main thing we did in lesson 4 was to categorize relations, right? We classified relations into 4 types. And what are these 4 types of relations we looked at? 1, So we are going to use mapping diagrams to classify the relations. We've already talked about this, so this is just an overview. So this was referred to as a one-to-one mapping or a one-to-one relation. And the reason why we call it a one-to-one is because every element in the domain maps onto exactly one element in the range. So that is a one-to-one relation or one-to-one mapping. The second one is, as you can see, is a many-to-one relation. And the reason we call it a many-to-one is because more than one element in the input map onto one element. So many from the input to one in the output. So this is called a many-to-one relation. Even here you can see there is only one element that the domain maps onto. So A maps only onto C. It turns out that B also maps onto C, but we are interested in what each element maps onto. So this is a many-into-one relation, as we talked about yesterday or in the previous lesson. Number 3 is what you'd refer to as a one mapping onto more than one. So one-to-many mapping or a one-to-many relation. Okay, this was a many-to-many relation, and why do we call it that? We can see A and B, that is 2, which is many, mapping onto a C, all right? Also, A and B mapping onto D, so that's many to one, but A by itself also maps onto C and D, so we can say that this is a one-to-many relation, and because of that, we have a many relation to many relation, okay? So a many to many relation. I need to look at this because we need it when we define functions. So let's move on now and see what functions are. Okay, so a formal definition for function is a relation. So those relations we've looked at, 4 of them, will qualify as a function if it obeys this formal definition. So a function is any relation in which every element in the domain maps onto exactly one element in the range. Okay? If that happens, then it is a function. Okay? All right. What does this mean? There are different ways of repeating this statement so that you can understand it. We are saying that every element in the domain maps onto exactly one element in the range. So another way of saying this is that each input must have exactly one output for us to refer to it as a domain. Okay, so these are the properties of a function. Every input has exactly one output. Another way to say that is no 2 or more outputs can exist for one input. Okay, it's basically saying the same thing. Which is to say that if a mapping, the ones we looked at in the previous, if a mapping ends with too many, so we had 1 to 1, then we had 1 to many. So if it ends with too many, then it's not a relation because it's mapping on more than one when a function is defined as any relation in which every input maps onto one output. So it has to map onto one output for it to be a function. So if it's mapping on too many, then it is not a function. Okay? If it is mapping on to one, then it is a function. Okay? So let's look at this and see what we have here. Which is a function here? A one-to-one relation. Is that a function or not? Well, it's ending onto 1. So it's 1 mapping onto 1, therefore that makes it a function. Okay? What about this one? A one-to-many relation is not a function because it's disqualified by this definition. We have to map onto 1, exactly 1 in the range for it to be a function. So this is disqualified as far as functions are related. What about a many-to-one relation? Well, each of those many, each of them only maps onto 1. And for that reason, it is accepted by the definition of a function and it qualifies. What about a many-to-many relation? Well, again, it's a to-many relation and therefore it is disqualified as a function. Okay, I hope you understand what the definition means there, but we are going to look at examples and be able to identify relations that qualify as functions. Okay, if a relation is presented as an ordered pair, so we are going to see relations in the various different forms of presentation and see how to identify functions from them. So we are starting with a relation presented to us as ordered pairs. How can we identify which ones are functions and which ones are not? Okay, so if a relation is presented as an ordered pair, the first thing we want to do is to focus only on the x coordinates. All right, ignore the y coordinates completely and focus only on the x coordinate. All right, and what do we say? If the set of ordered pair has different values of x, if the x values of those ordered pairs, if the x coordinates are different, then it is a function. That ordered pair qualifies as a function. If, however, an x value is repeated, okay, one ordered pair there has the same x value as another ordered pair. If that's the case, then it is not a function. We are going to look at an example right now, okay? So let's see. But in short, the y coordinates have no bearing completely on whether a function, whether a relation is a function or not. So we ignore the y coordinates completely. In other words, we deal only with the domain, we ignore the range, okay? Completely, to find out if a relation is a function or not. So here we go. Here's an example. We have a set of 6 ordered pairs, and our job is to find out which one is a function and which one is not. Remember, if the x values are all different, then we know it is a function. If any of the x values are repeated somewhere, then we know it is not a function. So let's look at the first one here. This is, the x value is a 1 there, 2, 0, nothing is repeated so far, -1, 4, -1 is now repeated, and 4 is now repeated again. There is a 4 here for x, and there is a 4 here for x. And so therefore, two values of x have been repeated. And because of that, by definition, this cannot be a function, okay? If x repeats itself, then the ordered pair is not a function. So we see there is an x there, -1 and -1 here, and the 4s are, we only need to see one case, but in this case there is also another repeat in 4 and 4 there, and because of this, this is not a function. Okay, you can pause the video and check the other 6 and see which one qualifies as a function and which doesn't. Let's see the second one now. That's a 3, -8, 0, -3, 6, -1, and 5. I don't see anything repeated there. You can check it again, but the values of x appear to be all different, and because of that, b is a function. Okay, let's go to C. So remember, if a value of x does not repeat itself, we know it is a function. If values of x repeat themselves along the line, we know it's not a function. Let's see number C, 10. So x is 10. Ignore the y values completely. So here we have 10, -16, 15, -4, and 6. I didn't see anything repeat there. 10, -16, 15, -4, and 6. Nothing has repeated, and therefore, I suppose this is a function. All right? The next one there, we have a 5, a 7, 0, -12. Nothing has repeated so far. 9, -6, and 8. Nothing has repeated itself, and that, therefore, has to be a function. All right? What about E? All right? We have a 5, a 3, a 5. There's a repeat. 5 is appearing twice. I can stop there. I already know this cannot be a function. I can check out and see if there is any other. There isn't any other, but this is enough to tell me that this is not a function. Okay? So 5 is appearing twice, and therefore this cannot be a function. You can see how we identify functions and non-functions from ordered pairs, a relation presented as ordered pairs. The last one there, we have 17, we have 10, we have 8. 8 is repeated. So clearly there is a repeat, and therefore this is not a function. Okay, I'm talking about the last one there, so that cannot be a function. So given a set of ordered pair as a relation, we can determine whether they belong to functions or not by just looking at the values of x and checking whether there is a repeat or not. As simple as that. Okay, let's move on. What about from mappings? If we are given mapping diagram, not ordered pairs now, but now we are given mapping diagram, can we tell whether a relation is a function or not? So, yes, we can. If a relation is presented as a mapping diagram, then once again, just like before, we focus on the x values, focus on the x coordinates, focus on the input, if you like, right? Or in the domain, all right? Focus on the domain. If more than one arrow branches off any of the x values, then the mapping is not a function. So we cannot have more than one arrow coming off a value in the domain. Okay? If we have more than one arrow, then that is not a function. Okay? Here is an example. Which of the following mapping diagrams represent a function? Here's the first one. Okay? If you look at that, in each case, in each value of the domain, there is only one arrow emanating that is coming out of the domain. Okay? Because of that, this is a function. Okay? This is how, in fact, this is a one-to-one mapping or a one-to-one relation. A one-to-one relation is a function. Okay? So this one has qualified. What about this one? All right? 0 maps onto a 0, but 2 maps onto 2 values in the range, and for that reason 2 arrows. This is a one-to-many mapping, and therefore it is disqualified as a function. So this is not a function. Okay? What about this one? Again, this is one-to-many. I don't need to look at the 2. I just need to see one of them, and that tells us that this is not a function. It is a relation, but it is not a function. All right? I hope that is easy to understand. Here is your turn. I have put 6 mapping diagrams there, and I want you to identify which ones of these are, which of the mappings represent functions. Okay? There we go. All right? I'll let it stick there for like 5 seconds, and then you can pause the video and check them out and identify 1 to 6 which ones are functions and which ones are not. Okay, let's move on so that we move a little faster. Okay, now we want to identify a function from a graph. If we are given a graph, how do we see whether that graph represents a function or not? All right, to do that, we use something called the vertical line test, also known as the pencil test. Okay, that means that if you have a curve like this, I'm going to demonstrate this shortly. If this is a curve representing some relation, values of x there and values of y there, values of y and values of x, we want to tell whether this is a function or not. You imagine holding your pencil, okay? You're holding a pencil vertically like that. Imagine your pencil extends to infinity on both sides. Okay, not to infinity, but at least covers the whole page, right? Then, if you move your pencil across like this, across the graph like that, if it is crossing your line, if it crosses your line only on one spot, now like this, if my pencil was somewhere here, if I place the pencil there, it is crossing only at that single point. If I put it here, it's crossing at a single point. If it is crossing only at one single point, then you know that that is a function. Okay? It is a function because that value of x has only one value of y. Therefore, that is a function. If this graph extended this way, suppose this graph here extended, suppose this graph went like that, okay? If it did that, then my vertical line now, if I extended my pencil, it would be crossing in two spots, okay? Two or more spots. If this one also came back this way, this is crossing in two spots, this is now crossing in three spots, all right? So the vertical line will cross at three different places here. We just need to see one instance where it's crossing in more than one place, and that will tell us that this is not a function, okay? So for it to be a function, the vertical line, that the imaginary vertical line or imaginary pencil should cross only at one spot for it to qualify as a function. And that's called the vertical line test, okay, for functions where we are given a graph. Okay, I'm going to demonstrate that shortly. Let's demonstrate that using GeoGebra. I believe I still have my GeoGebra file here. One moment, very quickly. There we go. I'll get rid of that and that. Yeah, one moment, and that. Okay, and now so what I have here is the dotted line is my pencil or my vertical line that's going to test. The vertical line can move to and fro, so I'm just going to animate it so it can move. I have set it to move between -10 and 10. Okay, so that's a vertical line moving across, and now we're going to test some functions with that vertical line. Okay, so here we go. My first function to test is going to be the equation y squared equals x plus 7. So that's that orange line you see there is the line y squared is x plus 7. Now, let's see. If we look at that line there, look at the vertical line. Okay, if you look at the vertical line, now the vertical line you can see is crossing at two spots, there and there. And that means, although this is a relation between y and x, the vertical line test says that it is not a function. Okay, for it to be a function, it cannot cross two points or more at the same time. So this is not a function as determined by our vertical line there. So the vertical line test tells us that the equation y squared is x plus 7 is not a function. Okay, let's try another one. We'll try one more. A few more. I think I had a number of them here. Let's try this one here. This is the equation of a straight line. The equation of a straight line. Does this qualify as a function? Let's see what the vertical line tells us. If the vertical line crosses at one spot, then of course it is a function. Otherwise, it is not. Okay, so the vertical line is crossing only at one spot, so every x value has exactly one y value, as you can see. An x value has exactly one y value. Every input maps onto exactly one output like that, and so this here is a function. So of course, the equation of a straight line is the linear function, so it is a function, definitely. We already know that. Let's see another one. One more. This is a familiar function. All of us should now know this. This is the quadratic relation. Is the quadratic relation a function? Do I need to move this slightly up like that? Yes. So the quadratic relation, one moment, you can see that it is crossing at one spot, but just in case you can't see that clearly, I will do that. And let's see now what happens when it comes back. Right? If it crosses, at the point of crossing, there should be a point. Yes. So it's crossing at one point there. You can see the purple dot. So that tells us that the quadratic relation, the equation is y is x squared minus 4. This is definitely a function. It's being crossed at one spot. Okay? This is the so-called vertical line test for functions. Let's see one more. This is the, look at this one here. Is that a function or not? Will the vertical line make it qualify as a function? Give it a moment. I want to... All right, it's crossing two places, but in fact it is crossing three places. Give it a moment. I'll put the next one there. This line, the vertical line, crosses this graph at three different places. You can see that, right? I can take it back, or I can do it manually. You can see there we are crossing at three different places. So it doesn't matter. Here we are crossing at one spot, and there we are crossing at one spot. But as long as this section here exists, we are crossing at three different places, and that disqualifies this relation here as a function. So this is not a function, definitely not, okay? It fails the vertical line test. The vertical line requires that it crosses only once, all right? Let's try one more. You will meet many of these functions that somebody may ask you to check. Yes. This is called the hyperbolic function, or the hyperbola. What about this one here? Is this a function? We try the vertical line test there. Does this qualify as a function? And I move my vertical line there. It is crossing at 2 points. Okay. Now it's kind of like one spot right at the end there, one spot. But because of that, the whole thing fails the vertical line test. And so the equation x squared minus y squared is 2 is not a function. All right. Remember yesterday in lesson 4, we discussed x squared plus y squared equals to 2, which was the equation of a circle. All right. Here is a bit of a difference because of that negative sign. So this is not equation of a circle anymore. All right. So therefore, this function is disqualified. It fails as it is not a function. It is a relation, but it is not a function. Okay. Where are we? Let me just move slightly there. Get rid of this. And we can do, I think we are done with them. All right. So the vertical line test can be used to determine whether a relation is a function or not. Okay. So we have used this to check whether a relation was a function or whether it is not. All right. So the vertical line test is used to check on whether a relation is a function or not. Okay. We focus on the x-axis. All right. If it is a discrete function and it crosses, remember what a discrete function is. We are going to check that out. A discrete function, if it is a graph, is just points on the grid. There are some points in there. So if a vertical line crosses 2 or more of those points, or touches 2 or more of those points at the same time, then it is not a function. Okay. If it is a continuous function, then it is a line. So if the graph crosses at more than 1 point or 1 point on the line, then it is not a function. Okay? So I have just shown you the simulation, so now we can move on. Here is your turn. Does this relation represent a function? So based on the simulation I've just shown you, I want you to tell me whether you think this is a function or not. Okay? Here is a relation R is x mapping onto an exponential function there. This is sometimes called as the Gaussian distribution graph. Is it a function or not? All right, I want you to find that out. Here is another one. This is a discrete distribution, discrete relation. Using the vertical line test, if the vertical line touches two of them at the same time, then it's not a function, otherwise it is. Okay, check that out and tell me what you think. Here is another one. This is an ellipse. Will it pass the vertical line test to determine whether it is or it's not a function? Here is another one. This is the graph of the cosine. This is a cosine graph from trigonometry. The question is it a function or is it just a mere relation? Okay. Here is another one. The relation, the equation of the relation is given there. That's how it looks. If you draw this graph, you can go and try it out. If you want to type this onto GeoGebra, don't put f of x. You just start by typing this immediately. So just type x squared minus 2xy cubed plus 1 over 10 is 1, and you will be able to see this. You will notice if you do that the graph is asymptotic about the y-axis on this side, same as on that side, okay? So, but the question is it a function or is it not? Okay, here is another one. This is a discrete relation. Will the vertical line test make this one pass? Will this relation pass the vertical line test? That's up to you. Here is another one. This is called a stepwise relation. Is this stepwise relation a function or not? Please notice that the unfilled circle there means it's not included. The filled circle means it is included. All right, so is that a function or not? Okay, the function notation is really straightforward. We recall the relation notation as R is such that X maps onto Y. We will not spend a lot of time here. We are towards the end now. Okay, so this is what we refer to as the relation notation. If a relation is a function, then we simply replace the R there with F. Okay, so when we see f, we know that we are referring to a function. Okay, not all relations are function, but all functions are relations. So we've already seen which ones would qualify as function. If the relation R above is a function, if this is a function, then all we do is remove that R there and replace with f. Okay, and we have that. All right, in this case, x refers to the values of the domain and y refers to the values of the range. Okay, so these are the elements inside the, those circles that we've been drawing for a mapping. These are the elements, all right? If that's the case, then these are the ones that we put here. So we can put a value of x1 there and it will give me a value of y1 and so on, right? Yes, in which case the function notation is then written as f is such that x maps onto. So this is maps onto, and we put a rule here. Okay, now that rule is represented by y, but we don't put the y there. Instead, we put f of x. We put f of x like this to say a function of x. Or we put the specific rule, the equation that is represented, like 2x plus 1, like e power x and whatever. Whatever it is that is the rule for the function of x, that is what we will put under here, and then this becomes the function notation. Yes? Pretty straightforward stuff. Still. Let's finish off. So, we replace the rule that I've already talked about this. So for example, if a function is such that x maps onto y, where y is represented by 2x plus 1, then we can remove the y and replace it with f of x, or put the rule itself, 2x plus 1, where 2x plus 1 is the value of the function expressed in terms of x. And so what we write? We write f is such that x maps onto f of x, which is y, by the way, or we can say f is such that x maps onto this, okay? And this is the function relation. Notice that today we simply, instead of writing this, in fact, when you see this, you just take this together like this thing here, take it together and refer to it as f of x, and remove that arrow there and put an equal sign and write 2x plus 1. This is how we write the function notation today. So both are valid function notation. So this, as well as what we've talked about here, is a function notation. Today, in today's world, we tend to use this form of notation, this one here. We already have it here, by the way. So today we tend to use this more than we use this, except perhaps in computer coding, programming, where this still makes a lot of sense. In terms of understanding, this notation is talking to you more, is communicating better than this. All right? This is meaningless except for those who have been seeing this before. It is kind of difficult to understand. But this one is kind of making the statement that a function is such that every x becomes, right? Every x maps onto 2x plus 1. So if I put value of x of 1, it's going to bring me 3 because x is 1 there. If I put a value of x of 5, it's going to give me 11, right? Like that. So this is more communicative, but we are now used to writing it like this, which is still fine. Either way, if you write it like this or write it like that, we will all be happy. So, well, you already know then that you have known the function notation for a very long time. As long as you knew this, if you knew how to write this, then you are already writing using function notation. Excuse me. All right, let's move on. Here is an example. Now we are evaluating functions. Now that we know how to write the function notation, we can now evaluate. Now remember that writing this is the same as saying, it's equivalent to saying f of x is the same as 2x squared minus 1. So this is another way we could have written that. So anytime you see this, please remember it means that. Now we are being asked for f of 0. That means if we input 0, what do we get on the output? All right? If you're taking computer programming, you can understand why I said this notation makes sense, right? You input 0, what should we get out there? Well, we put a 0 there. 0 squared is 0 times 2 is 0. So f of 0, we end up with negative 1 there. All right, so f of 0, input 0 there. All right, we get, it's the same, f of 0 is this, which is negative 1. So we can say f of 0 is negative 1. Okay, we are evaluating functions. We have evaluated f of x for x equals 0. What about f of x where x is negative 1? We do the same thing. Now I'll jump a step. All right, f of negative 1, we substitute negative 1 in there. Remember, negative 1 into bracket like that. So the square goes to the negative as well. Because the power is even, this whole thing becomes positive. Positive 1 times 2 is 2. 2 minus 1 is 1. So f of negative 1 is 1. All right, what about f of k? Part 3 there. F of k, we input k, so it becomes 2k squared minus 1. We can't simplify that any further, so we will just write that as f of k is 2k squared minus 1. It is that simple. Okay? Here's another one, this time given as a graph. Example 2. The graph on the side, I removed it from, it was below and I removed it. The graph on the side represents a function g of x. So although we use f to represent functions, sometimes we can use other symbols, especially when we have too many functions on the same page. It is okay to remove f and replace with a g or a small letter h or even a small letter r, not capital R, small letter r. Can be used to represent a function. Okay, so don't be bothered by this, that it is not f, and we say the function should be f. All right, so the graph below represents a function g of x. Use the graph to evaluate g of -5. So to evaluate -5, remember, it's a function. We go to the x-axis. So we always go to the x-axis and look for a value of x of -5. So if we look for a value of x of -5, -5 is right there. Once we get there, we do the vertical line. So we move a vertical line until we can cross the graph itself. When we get to the graph, we read across onto the y-axis. Okay, and that tells me a 4. So therefore, f of -5 has to be 4. So f of g of -5 rather is 4. Let's do the same for 0. We are looking for g of an x value of 0. So the input is 0. What's the output? If we put 0, we go search for 0 on the x-axis. 0 is there. Okay. Then we draw a line searching for a vertical line searching for our graph there. So draw a vertical line. I hope you've seen that. Hope you see the vertical line. I didn't make it very clear there. All right. When we cross the graph, we identify the point. It is 2. Well, we should be moving across to meet the graph, but we've already reached the graph by just moving vertically, so we don't need to move across anymore. So our value already there is 2, and therefore g of 0 is 2. Okay? G of 0 is 2. Next, what is g of 5? So again, we go to the x-axis and look for 5. The value of x of 5. We move vertically so that we meet the graph, but we don't need to move because the graph is already passing through that point. So all we are left to do is to move horizontally until we cross the y-axis. So we do that, and where we cross the y-axis, that must be the output, which is 0 in this case. Okay, and so g of 5 is 0. It's as simple as that. All right, next question is to express the function using a function notation. That means we want to write f is such that. We want to write f is such that x maps onto some rule here. So we need to find this rule. That rule is in fact the equation of this line. So if we're going to get the rule, then we have to determine the equation of the line. How do we find the equation of a straight line? It's pretty straightforward, especially in this case because we have grids on the graph. If we didn't have grids on the graph, we would need to know the coordinates of 2 points. But now we have these grid lines here. That means I only need to pick some strategic points. I go and pick the point 0, 2 rather, and 5, 0. So if I start at 0, 2, I start by moving in the positive x direction. So how many steps do I move in the positive x direction to get here? You should see that I will move, if I start right here, I will move horizontally 5 steps. So there is a positive 5 steps in the x direction, and I need to get to this point. So the next part is to move vertically. I'm not going up, I'm going down 2 steps. So it's -2 steps in the y direction. And so my gradient is -2 over 5. Yeah? We did a question like this before in the previous lessons. So I hope this makes sense. All right. So if we are going to find the equation of this line, the first step is to find the gradient of this line, and we have found that as -2 over 5 there, right? The gradient is negative 2 over 5. The next thing that we need to find is to pick a point, a strategic point whose coordinates are simple to see. One of them is that, all right, 0, 2. 0, 2 is very nice. Coordinates such that one of them is 0. The other one is here. It would be 5, 0. Okay, so we can take that or we can take this one here. Okay, let's pick this one. And the coordinates of the point is going to be AB. So that AB there, if we pick this point, let that be 0, 2. Okay, once we have those two, that's all really we need. We use the formula y minus b is always the gradient into x minus a. Y minus b is m into x minus a, always. This is way faster. We get it in one step. Instead of trying to look for the gradient first, you know, m is y2 minus y1 divided by x2 minus x1, and then after we found the gradient, then we have to substitute into the formula y is mx plus c to find c, and then, you know, substitute back to get the equation of the line. That takes a bit too long, and for a student who wants to sit an exam, a 2-hour exam, where there is no time, you want methods that can get you to the answer much faster. And if you can remember this, anyway, this really comes from m equals, like I told you before, this comes from m is y1 minus y2 minus y1 over x2 minus x1. If you rearrange this, you can see you get y2 minus y1 is m into x2 minus x1. So this, you can see, y2 minus y1. So if we let x1, y1 be these coordinates we are talking about, the a and b, the one I'm talking about here, then you can see that this really is just the same as what I've written here. So instead of trying to do this, rearrange it so that it looks like this, and just write this. Okay, so you have the gradient and you know the coordinates of one point through which the line is passing. So all I have to do now is to substitute that in here. Okay, so I'm going to say y minus 2, because the value of y there is 2, must be equal to the gradient, which I have also, into x minus 0, because the x coordinate there is 0. The same thing would occur if I pick this point here. This point is the point 5, 0. So the value of x now is 5, but the value of y is 0. So I would put 0 there, okay, and I would put 5 here. And if I rearrange, I would still get the same answer. All right, but I choose this because it gives me my answer much faster than even this one. All right, so let's see. Substituting the values of a and b, our a is 0, our b is 2 there. So if we substitute that, write it on this side, we have y minus 2 is minus 2 over 5, which was the gradient, into bracket x minus 0. This disappears, so if we rearrange, we only left with minus 2 over 5x, and that negative 2 comes to this side and becomes plus. So the equation of this line is, in fact, the line y is minus 2 over 5x plus 2. And because of that, now we can write our relation notation and say f is such that x maps onto the rule, which is the function itself. I hope you've understood this, that it wasn't so unforgiving. All right, here is your turn. I want you to answer that question. I will not even read it. I give you a chance to, you will pause the video, read it, and try it out. Okay, that is example 3. Example 4 as well is yours. You're given the domain. Your task is to take values of the domain, input here. So if x is negative 5, y is going to be what? 8 times negative 5 is negative 40, minus 40 minus 12 is minus 52. So the output, if this is negative 5, the output is negative 52. If this is negative 2, put it in there and see what happens. If this is 0, put that in. So I want you to do that for the 3 functions. So these are confirmed functions. We are no longer talking relations, okay? I hope you know what these vertical lines mean. If you don't, let me know and we can discuss that. All right, here is another one, but I think we will do this one. The graph of the function y is f of x below show the temperature outside at different time over a 24-hour period, right? So ignore this side of the graph does not exist. Time starts here, okay? So between 0 and 24 hours later, the temperature increases to a maximum and then drops again to 0, right? So what's the question? Which is the independent variable for this case? Which one is the independent and which one is the dependent variable? You can pause and think about it for a moment, but it should really be straightforward. I'm writing the answer now. So the x, the one on the horizontal axis, is the independent variable. What goes on the y-axis is the dependent variable. So the independent variable is also the input. It's also the domain. The one that goes onto the y-axis is the dependent variable. It is also called the range, all right? It is also called the output, okay? So at time this, when we input a time of 12, the output is 35, and so on, huh? When the input is, what is that? When the input is 5 hours, in other words, we want to know what the temperature is going to be at 5 in the morning. Well, we go up and the temperature is going to be 20 and so on, right? So the temperature, we put in the time and it tells us what the temperature is going to be. That's the relation. So the independent variable is the time and the dependent variable there, as you can see, is the temperature. Okay? What else is there? Part B, explain whether or not this is a discrete function. Well, clearly this is not a discrete function. It is a continuous function. How do we define continuous function? If between the interval of 0 and 24, or the interval that we are talking about, okay, the line is continuous. There is a continuous line, whether it's going up and down or just going up or whatever way, but it is a continuous unbroken line, then we are talking about a continuous relation or a continuous function in this case. So therefore, this is a continuous function because we are having a continuous graph line in the time interval 0 to 26 hours. All right, so it is a continuous function, which is a continuous relation. All right, part C, which of the following would find the temperature at 10 hours? All right, so if we put 10 hours, so 10 hours, remember, is the input, we get an output. Which expressions here will help us determine the temperature at 10 hours? All right, we are given the input, which normally goes inside the bracket. Therefore, the answer to this question is the second one there. Okay, f of 10. What's the value of the function when x is 10? Okay, so that's it. Part D, which of the following would find the time when the temperature is 10 degrees? So now we are given the output, we are looking for the input. Obviously, this would be A, or the first one there. This should remind you of some of the things we've talked about already. Remember when we were talking about, say, the population of prey, or predator and prey. The population of rabbit at some time t is given by, maybe 10 e power minus 3t, where t is the time, okay? And we are told there is a time when the population will be 1,000. So you say, well, when is the population going to be 1,000? That means you are given this side, 1,000, you want to find the value of t, all right? So that's the same as P of t is 1,000, find t, all right? We are looking for the time, okay? So in this case, you know what we would have to do, all right, to find it. And therefore, this is the function similar to this, for which we would be able to find the temperature, not the temperature, but the time when the temperature is 10 degrees Fahrenheit. Okay, the unit there for temperature, as you can see, is Fahrenheit. So you can imagine where this question came from. The guys who still love to use The Fahrenheit temperature scale is the US, of course. All right, so that's that. We are very, very close to the end. Here is a comment on mathematical notation. I think I've already talked about it anyway. And that is the fact that these two are both notations for functions. So they are both function notation. Today we tend to use this more than that, but for students who are learning programming, it's more likely that you will use this when you're programming. You're likely to be talking about input and output and putting an expression for the output like that. Okay, but they are both valid either way. This tends to be, we think of it as an old symbol for an old function notation. Okay, so that is the comment on that. But otherwise, here are the questions I want you to go and look at. This is our ebook, Haese for MYP5, the second edition, Haese Plus. Okay, so this is the extended math class. It is also referred to as the pre-IB textbook. This is the core material for anyone studying SL and HL in the diploma program. We don't teach this material in the diploma program, so I want you to solve this problem so that you are prepared well. From page 329 to page 333, those 4 exercises, okay? Otherwise, this will be the end of lesson number 5. I hope you were able to follow and that you liked it. Please like the video so that when lesson 6 comes through, you will be notified. Thank you very much for watching. Remember to ask me questions if you have any. All right, otherwise, see you for the next video. All right, thank you and bye.